Today we want to prove a theorem whose statement is quite intuitive and easy to understand, but actually the proof is a little bit involved. But nevertheless, it's interesting and worthwhile. And this theorem goes by the name of Borsuk-Ulam. Okay, so what does the theorem say? It says that whenever you have a continuous map from the n sphere to the n-dimensional Euclidean space, then you know that two antipodal points on that sphere must map to the same point in Euclidean space. So for every continuous map, and of course it's our convention that we do not need to say continuous, so I just write r to the n to as n to r to the n here. For each such continuous map, there exists some x in Sn such that f of x is equal to f of minus x. Yeah. And you might remember from a couple of videos ago where we already had a statement about the weather that follows from topology. That was a statement that at any time, at some point on Earth, there's calm, the wind does not blow. And there's a second statement about the weather which we can deduce from this theorem here, namely in case n equals 2. So when S2 here is, of course, greatly pictured by the surface of Earth. In this case, well, the function goes to r to the 2. And the function could, for example, be just the function that carries each point on Earth to the temperature and the air pressure, which is dominating at that point at that time. And it is fair to say that this should be a continuous map. And then the statement of the theorem is that there exist two opposite locations on the surface of Earth, which have precisely the same temperature and the same air pressure at the same time. And I think this is a fascinating statement, which you wouldn't immediately say is true, but it follows from this theorem. I mean, right now it's January in Germany, it's minus 6 degrees outside. The antipodal point is somewhere in the South Pacific, outside New Zealand, and I guess it's warmer there. So my guess would be that the point where we are right now, it's not the point which will have the same value as the antipodal point. But somewhere on Earth, even at this moment, these 2 points exist. And this is so nice that I think I do want to write down this statement so that everybody has a record of it also in the notes. So it means that at any time there exist two opposite points on Earth or say opposite locations on Earth with the same temperature and air pressure. All right, so this is some real-life motivation for a topological theorem, and this should be motivation enough to enter the proof. And actually, the theorem of Borsuk-Ulam is only one in a whole family of theorems which have similar or related statements. And this is also the way we want to prove this theorem. Namely, what we will really prove is the so-called Antipode theorem. And I will state this theorem right now, and then the concept of this video is to first see that the Antipode theorem implies the Borsuk-Ulam theorem, and afterwards we will prove the Antipode theorem. So what does this say? It says if you have a map now from the n sphere, the n-dimensional sphere, to the m-dimensional sphere, so these can be different dimensions, and if this map is equivariant with respect to the antipodal map, yeah? So meaning if I consider the value of g at the antipode of some point, then I get the so sort of the minus of the value, the antipode point of the point value. So g of minus x equals minus g of x. This is what I mean. And if such a function exists, so satisfies this relation for all x in Sn, then we can conclude that actually the first sphere here must be of lower dimension than the second sphere. So then n is less or equal to m. Okay, so one possible way to construct such a function g is, well, Sn lies in R to the n plus 1, Sm lies in R to the m plus 1. So you could consider an isometry. Yeah? So a linear map from R to the n plus 1 to R to the m plus 1, which preserves the scalar product. Then this map will also preserve the sphere, so it will map Sn to Sn to Sm. And it, of course, does satisfy this relation here just because it's a linear map. Yeah? So this would be one example. But you can see that this construction breaks down in case n is bigger than m, because then a linear map will automatically have to have kernel. And if you have kernel, then some vector will be mapped to 0, so we don't get an induced map on the spheres. So this is maybe already some indication why this should be true. But we will see the proof in a bit. But like I said, we will start by first verifying that actually the antipode theorem does imply the Borsuk-Ulam theorem. So antipode implies Borsuk-Ulam. And well, so we want to prove the Borsuk-Ulam theorem. So the statement, what we need to prove is we have a function f from S to the n to R to the n. We need to show that there exist two antipodal points mapping to the same point. And we do this as a proof by contradiction. So suppose actually f has the property that f of x is not equal to f of minus x for all points on the sphere. And then, of course, the idea is then that out of this map f, we now construct a map G, which is in contradiction to the antipode theorem. And how do we do this? Well, we take G now from Sn going to Sn minus 1, namely G, well, f went from Sn to R to the n, and now we will normalize suitably a map such that we end up in S to the n minus 1, and we do this like this. Well, we take this difference of which we know no, it's nowhere 0. Yeah, that's the condition we had up here. And we just normalize this. Yeah, so we divide by the norm of this vector. And our assumption that this inequality holds true everywhere means that we do not divide by 0 here. So this is actually really a well-defined map going to Sn minus 1. But this now does satisfy the relevant relation that g minus x is equal to minus g of x, yeah, because if we put in minus x here, then these arguments here sort of are swapped. In other words, I can undo this by changing the sign, so that's why this equivariance with respect to the antipodal map is satisfied. And this, of course, is already a contradiction. Yeah, because the first sphere here is of higher dimension than the second sphere, so this cannot exist if the antipode theorem is true. Okay. So far, so good. So we're now ready to go into the proof of the antipode theorem. Okay. Proof antipode theorem. Okay, so to do so, let's first of all pick some singular p simplex. So delta p going to rp to the n. And you might now wonder, what does this have to do with spheres? Well, the spheres enter now our consideration because they are the universal covering of real projective space here. And actually it's also covering theory which we will use here to conclude that every such singular p simplex has precisely two lifts to the universal covering. Namely, let's just draw it as a lift. So we here got the map from delta p to rp to the n. And here we've got our universal covering, which is the n-sphere. And now you remember from last semester, we had the lifting criterion, which said such a continuous map here can be lifted to the covering if it happens that the fundamental group here is mapped into the fundamental group, into the image of this morphism here on the level of fundamental groups. And this is, of course, an empty condition in this case because delta p is a contractible space, so it does not have any fundamental group. So that's definitely verified. And there was also a uniqueness statement about lifting in the lifting criterion. And this said that once you fix base points and require that the base points are preserved in this commuting triangle, then the lifts are unique. But if you fix base points down here, so point here mapping to some point here, then there are two possible points you can fix upstairs here because it's a twofold covering, and corresponding to these two base points you get two different lifts. And let's denote these two lifts by, well, sigma bar plus and sigma bar minus. Plus minus referring to either of these two arrows. So whenever we have a singular simplex in real projective n space, we've got precisely two lifts to the n sphere. And the second information is that these two lifts are actually swapped by the deck transformation action. By the deck transformation action of the group with two elements here on the n sphere. Yeah. So the deck transformation action corresponding to this covering is simply the one that maps, so the non-trivial element of this group with two elements maps each point in Sn to the opposite point. Yeah, this is precisely the deck transformation action, and this map swaps the two possible choices of lifts here. Yeah? And this observation leads us to the definition of a chain map of singular chain complexes. And this works like this. So because of this, we obtain a chain map, call it tau star. And this starts at the singular chain complex of Rpn. And now something we have, I guess, never really done so before in applications happens. Then we do not take z coefficients, we take z mod 2 coefficients. Yeah? So maybe let me draw this, move this down here to have more space. Let's try again. So we obtain a chain map from the singular chain complex of Rpn with coefficients in z mod 2 going to, now my pen, how do I get it back? Let's see. Yeah, going to the singular chain complex of the n sphere, again with coefficients in z mod 2. And, well, how does this work? I take some simplex here, let's call it sigma, some p simplex, and this maps to, well, I've got two possible lifts to the n sphere, and I just take the sum. So this goes to sigma bar plus plus sigma bar minus. Okay? And, well, I can definitely define it like this. The question is, why is it actually a chain map? And, well, the chain map condition, what does it say in this case? Well, it says that if you have such a simplex, or, well, you have a chain of simplices, but just consider one simplex, and you take the boundary of this simplex, yeah, then you get a bunch, like a chain of boundary faces, and the two lifts of those boundary faces, this is precisely the same thing as if you had lifted the whole simplex and then, I mean, as if you had taken the two lifts of the whole simplex and then taken the boundary faces. Yeah, that gives you the same thing. And this is precisely the commutativity you need to get a chain map. So this is clearly a chain map, and it also has a name. It's called transfer. Okay. And now this chain map, I claim next, actually sits in a short exact sequence of chain complexes. And how does that work? Well, first of all, here in the middle, I've got the singular chain complex, so I shall allow myself to drop the letter sing on top now to be more lazy. And in the middle, you have the singular chain complex of Sn with coefficients in Z mod 2. And here you definitely get a chain map induced just from the covering projection. Yeah? So you get C star of P, where P is just the map from Sn to Rpn. So you get this one to Rpn with coefficients in Z mod 2. And this chain map is obviously surjective, so I can draw a zero arrow at the end, because, well, whenever I have some singular simplex here in Rp to the n, then a lift does exist. Yeah, this was the lifting criterion we just used, and this lift does provide a pre-image for this chain map. So this is clearly surjective, and the question is, what is the kernel of this map? And, well, when does it happen that if you have some chain of p simplices here, which maps to 0 here, well, if you've got one p simplex in this chain, you push it down by p to Rp to the n, and in order that this simplex now cancels out, the only way that this can happen is that also the other lift of this simplex sits inside this chain. Yeah? Because coefficients are in Z mod 2, so each simplex either is contained in the chain or it's not contained in the chain. Yeah? And the only way that something can cancel here is that both those simplices up here are contained in the chain, yeah? So that they map to the same one and then they cancel out to 0. So this says precisely that actually the kernel of this map is the image of the transfer map. Yeah, and therefore we get...
Did you also explain the other way around, that the composition is 0? You said if something is in the kernel, it comes from tau.
Yes.
But the other way around is even easier, right? If you
so
compose it, you get 2 times 6.
Exactly. So if you start with If you start with a chain and you form follow the compositions, you get every simplex twice, and 2 is 0 in our coefficient ring. Yeah. Right. And I mean, this is also injective. If you have a simplex here and you map it to the sum of the two simplices in Sn, this is not going to cancel out because those are two different simplices, these two lifts. Yeah. Right. So we obtain a short exact sequence of chain complexes here, and actually, so I think I really have to adjust a bit my drawing. Can I do it still? No, I think it's fine, yeah. So actually I do not only get a short exact sequence of these chain complexes, but if I have in addition my map G from the statement of the Antipode theorem, then I actually get a whole map of short exact sequences of chain complexes. So let's give ourselves this map. So let G be a continuous map from Sn to Sm with the property that G minus x equals minus G of x. Then, well, first of all, I can repeat the same short exact sequence of chain complexes with the m-dimensional projective space and m-dimensional sphere. So let me just copy the line, changing n by m, Rpm, C mod 2. And here I've got my transfer map going to C star Sm, C mod 2. Then comes the map induced by the projection to Rpm Z mod 2. And again, I have a 0 here. Then right. Then here I've got the induced map on the level of chain complexes from G. So this is just C star G. And if I have such a map here, which with the property G of minus x is equal to minus g of x, then this is precisely the condition that I need such that this map G descends to a map of the corresponding projective spaces. So that I get a map from Rpn to Rpm. And this map I want to call G bar, and this is the one I can put here. So this is C star of G bar, and the same here. Yeah? C star of G bar, and well, let me write down here what I mean with G bar. Well, G bar is a map now from Rpn to Rpm. And it's defined, well, an element now in real projective n space that's an equivalence class consisting of 2 points in the n sphere, so I just write it as plus minus x. And if I take G bar of such an element, well, then I just get plus minus G without bar of x. Yeah, and this is now well defined because no matter which representative I take here for putting inside, it will only differ by a sign, but the sign doesn't matter anyway, right? Because this is what we mod out here. We take each element and its opposite one. So this is this induced continuous map, which completes this diagram of short exact sequences, this map of short exact sequences. And we now want to discuss that this actually does commute. And well, that's pretty clear for this square here, because this just commutes on the level of spaces, yeah? I mean, it commutes on the level of spaces. So we had here the map from Sn to Sm, and this was precisely the descendant map here. So together with these covering projection, this is just, the reason is just that C star is a functor, so this does commute, because it commutes on the level of spaces. And the more interesting part is this square here. So now the other one works, okay. So still to be verified is the fact that this left-hand square also commutes. And let me give you a reason why that is true. So star commutes because we can again consider a square on the level of spaces, but it's not quite so easy that one can just say C star is a functor and therefore it commutes. One has to argue a bit differently because now the arrows go in the wrong direction. Yeah, so we have Rpn on the left-hand side. And now, of course, the covering map goes from right to left, from Sn, and here we've got Rpm, and the covering map coming from Sm, and here we've got G, and here we've got G bar. Okay. And now we want to prove that, well, that this square here commutes, so we should start with a singular simplex in Rpn, so in reprojective n-dimensional space here. So let's just write one here, delta p continuous map to Rpn. And then we have the following little computation. If we take now the lifts, the two lifts of this simplex, so that's sigma plus minus bar. So these now live in Sn, and if we now apply G here to push these simplices over to Sm, and afterwards we push them down to Rpm with this covering projection map, so to indicate the dimension, let's call this one Pn and this one Pm. So if I apply Pm to these pushed over lifted simplices, then, of course, composition of maps is associative, so I can also form this composition in this order, Pm circ G circ sigma plus minus bar. And now Pm after G, well, that's just this composition here. That's by commutativity of this square of spaces. It's the same as G bar after Pn. And then sigma plus minus bar. And now, of course, I can go back with my order of composition. So that's the same as G bar of Pn sigma plus minus bar. But now sigma plus minus bar, these were precisely the lifts of the original simplex sigma. I mean, I should have called this sigma right away. Yeah, it's this similar p simplex. So no matter if it's plus or minus here, this is just the composition G bar after sigma. Okay, and what does this little computation say in words? Well, it says if I have a simplex sigma, so living here in this space, and I move it over by G bar down to RPM, it's the right-hand side here, then what I get is the lifts under PM, so the lifts under this map here, these are precisely the pushed over lifts of the original simplex under PM. And this statement is precisely saying that the square up here commutes. Yeah? So lifting the two simplices here right away, move them over, that's the same thing as lifting the original as moving the original simplex down to the other projective space and then considering the two lifts. So we verified that we have two short exact sequences of chain complexes, this one, and we've got a map of those short exact sequences of chain complexes, meaning these three arrows here such that everything commutes. And we already know that a short exact sequence of chain complexes induces a long exact sequence in homology. So since we've got two such short exact sequences, we get two such long exact sequences in homology. And there was a naturality statement in this theorem saying that, well, if we have these two long exact sequences in homology, and then the map between the short exact sequences of chain complexes also induces maps between these long exact sequences in homology. In other words, we obtain a commutative ladder of long exact homology sequences. So let's just put this down here. We obtain a commutative ladder of long exact sequences in homology. And of this commutative ladder, we will now just consider one portion, namely the lower long exact sequence in homology. Yeah, this is the one I want to picture now. So since it's corresponding, sorry, I already made it disappear. Since it's corresponding to the lower line here in our map of short exact sequences, which is drawn red, I also want to draw it in red. So the lower long exact sequence in the commutative ladder looks then like this. Okay, let's start with HM-RPM with coefficients in C mod 2. Yeah, so that's the homology group corresponding to the left-hand chain complex. Then in the middle we've got HM-SM coefficients in C mod 2. And then we've got let me try to draw this a little closer. Like this maybe, okay. And then we've got the right-hand chain complex, the corresponding homology is again HM of the reprojective space, RPM, coefficient in Z mod 2. Okay. And then, since this is now a long exact sequence, the whole picture continues now, and maybe I'll try to be so lazy as to just copy this and then change the indices accordingly. So, and yeah, I also should write down the morphisms here. So this is the map induced in homology from the chain map tau star, from the transfer map, and this is the map induced in homology from the covering space projection. So I think we called it PM, yeah? The M referring to the dimension of sphere and projective space. Okay, so here we've got the same thing in 1 degree lower. All right, and now this long exact sequence carries on and on and on, and it ends in the end in degree 0. So let's put it again here. All right. Okay, so the boundary homomorphisms in this long exact sequence in homology, these are the ones snaking around here from from the right-hand side. Yeah, so this is the boundary homomorphism, this is the boundary homomorphism, and going here. Yeah. Okay. So now the game is the usual one in algebraic topology. We want to identify all possible terms in this long exact sequence and draw conclusions from this. Yeah. So let's do that. Change the color again. So first things first, I would like to conclude that this arrow here is the 0 arrow, the first arrow appearing here in this portion of the long exact sequence. And to do so, well, I would have to consider the previous object, which would now be the m plus first homology of real projective M space. So let's put down a little observation down here. Observation. And well, if I consider the m plus first degree homology of Rpm with coefficients in C mod 2, then that's actually 0. Okay, so well, later on we will get to know cellular homology, and then the reason why this is 0 will just be that this is an m-dimensional CW complex, so it doesn't have m plus first dimensional homology. But since we do not have available this 2 right now, we can also argue differently. And what we could do here is we could consider the Meyer-Vitoris sequence of the following push-out diagram, namely the one giving the CW structure of real projective space. This was explained in a previous video in German last semester, and this structure is the following. So if we have Rpm inductively already defined, I mean Rpm minus 1 already defined, then how do I get Rpm? Well, I've got the universal covering map here from the m minus 1 sphere going to Rpm minus 1. And I use this covering map just as the gluing map of a new M disk, which I attach to the space. Yeah? And then the push out I obtain from this input data, this is precisely Rpm. Okay, and if you now consider the Meyer-Vitoris sequence associated with this push out, then you will find out inductively that actually also this higher homology group must be 0. So what you would get here is that the m plus first homology of Rpm must be equal to 0 if the m plus first homology of Rpm minus 1 is 0, and so on. And if you go all the way through until Rp0, you just get a point, and then you will know that the m plus first homology of a point is 0, and from this you get it. Yeah. So like I said, this is later on. This will be almost something trivial, but right now one would have to argue like this with the Meyer-Vitoris sequence. Okay. So long story short, the previous object in this long exact sequence here is 0, and therefore also this arrow here must be 0. All right. Next thing we want to see is, well, can we identify the next 2 arrows here? And to do so, what we will do is we will not consider this composition as it's drawn here. So first transfer, then the covering projection map, but we'll consider the reverse composition. First the covering map and then the transfer map, and see what happens. So this was observation 1. Let's now do observation 2. So if I consider the second composition, so that would be Hm of the transfer after Hm of the covering projection, then, well, what does this composition do? Well, I take a singular M cycle now representing such an M-dimensional homology class now in the M sphere, yeah, and I push it down by the covering map to the M-dimensional projective space. And afterwards I take transfer, meaning I take now the sum of the 2 lifts of this push-down cycle. So what do I get? Well, first of all, I get the cycle I started with, but then I get the other one, yeah, the moved one by the deck transformation operation. So what I get here is, this composition is first of all the identity on the M homology of Sm. Yeah, I mean, push down and lift will first of all give you the original one, but it will also give you the other one, the deck transformed cycle. And this, well, how do I write this as a map? Well, I get the original one and I get the image of the map induced in homology of the deck transformation action. So this would be the map SM, whoops, which maps x to minus x here. Yeah. So push down and the two lifts give you the first one and the other one, the deck transformed one. And now, well, the first one I just copy, it's the identity. And how do we argue here? Well, this map from SM to SM, which maps each point to its antipodal points, that's above all a homeomorphism, right? I mean, has a continuous inverse, namely itself. So that's a homeomorphism, and HM is a functor. Yeah? So HM must map a homeomorphism to an isomorphism. But now remember, we're considering homology here with coefficients in Z mod 2, and we already know that the mth homology of the M sphere, that is just Z mod 2. And there's only one isomorphism from Z mod 2 to itself. It's the identity. Yeah? So therefore also the second summand is the identity. And what we actually get here is twice the identity, but 2 times the identity, that's 0 times the identity with Z mod 2 coefficients. So therefore this is 0. Yeah, so let me just write in brackets here Z mod 2 coefficients. Okay, so now we know this composition is 0, but we also know that what we just discussed, we have a 0 up here, and therefore the succeeding arrow must be injective. So HM's tau star, the map induced in homology from transfer, is an injective morphism, and therefore this composition can only be 0 if already the first one was 0. Yeah, the second one is trivial kernel, so HMPM is actually 0 is what comes out of this. So let's add this new information to our long exact sequence. Yeah, this one must be 0. I have the correct pen here, let's see. This one is the 0 arrow, and now we see that this arrow sits in between 2 0 arrows, and therefore it's an isomorphism. Okay, so far so good. So we already identified a couple of arrows here. Next thing we see, or we get very cheaply, is here we've got the M sphere, and we already know the homology of the M sphere. It doesn't have any homology in degrees strictly between M and 0. So therefore, this object, the whole object, is 0, and therefore the arrow ending and starting in this object are also 0. Okay, so that's good news, because that means, since this is always going to be zeros here, yeah, so here in the middle there will always be zeros in this whole middle portion, that means that all those boundary homomorphisms must be isomorphisms, yeah, because they now sit between 2 0 maps. So therefore this is an isomorphism, and well, it's the same arrow as this one, and this one will also be an isomorphism, and so on and so forth, and we only have to be a bit more careful in degree 0 when this long exact sequence ends. Yeah, but there we can argue similarly, because this last arrow again is, well, it's just, let me draw it in red, induced by the covering projection. This is H0 of P, and well, it's just a continuous map of 2 path-connected spaces, and then we already know that in degree 0 this induces an isomorphism. Yeah? I don't know if it was an exercise or if we did it in the lecture. But either way, we know that this must be an isomorphism. In particular, it's injective, so the preceding arrow must be 0. And therefore, we even know in the last degree, where the boundary map goes from first homology to 0th homology, even in that case, it's sitting between 2 zeros, and therefore it's also an isomorphism. All right, so what we gain from this is that actually all those boundary homomorphisms between, in degree lower than M are isomorphisms. And this will now come in handy in our conclusion of the proof. Namely, from this we get the following. So in case our 2 relevant dimensions are related like this, so n is at least as big as m, we thus get the following. Well, we've got our first boundary homomorphism, or I mean highest degree boundary homomorphism of which we know it's an isomorphism, so that's the mth degree of RPM coefficients in Z mod 2. And well, this boundary homomorphism goes to the m minus first homology of RPM with coefficients in Z mod 2. And now if n is at least as big as m, then we can repeat, of course, the whole argument for the upper part, the upper long exact sequence of our ladder. I mean, that's just now n-dimensional space, projective space, and the n-dimensional sphere. The same thing applies. So as long as n is at least as big as m, we get a corresponding isomorphism for the boundary. Sorry, here it's m, of course, and here it's n. For the boundary homomorphism of a real projective n space. So this goes here to 1 degree lower, m minus first homology of RPN. Yeah, so this is just precisely the same argument as before, just using n is at least as big as m. So we've got these two boundary isomorphisms, and they are now related because we've got a commutative ladder. So here we've got our map induced in mth homology from our map G bar, and here we've got the map, well, again, induced in m minus first homology of G bar. Yeah, so this square is just one portion of the commutative ladder, and we now know the horizontal maps are isomorphisms. Yeah, and the good thing is, well, we have this square here for all degrees smaller than m, so we can just continue like this with just juxtaposing, how's it called? Concatenating those squares one after the other, and then we get more and more isomorphisms. So the next one would go to m minus 2 and so on and so forth. And it will finally end in degree 0, where we then got h0 of RPN. So I'm going to leave out the coefficients here because I'm running out of space. Like this. And then I will go to h0 RP m here. And again, the map h0 G bar here. This is again a map induced from it's a morphism induced from a continuous map of path-connected spaces. So that does also induce an isomorphism. Yeah. So using all these boundary isomorphisms, what we get is we could factorize the map HMG bar just through a bunch of isomorphisms, going all the way to the right and going all the way back to the left. So conclusion is that also this map HMG bar is actually an isomorphism. So hence HMG bar is an isomorphism as well. And now from this we can actually conclude the proof, because this map HMG bar does not only sit in the square with the boundary homomorphisms, but it also sits in the square with the transfer homomorphisms. And if we consider this square, so it's from our HM RPM Z mod 2 going to, sorry, I now have to be really careful about my m's and my n's. Yeah, so the upper one is an n, and the lower one is n. Here it's m, but projective space is now also m-dimensional. So here I've got this arrow of which we've just shown it's an isomorphism, HMG bar. It's an isomorphism. And here we've got the transfer map. Yeah, so this is now going to HM of Sn, Z mod 2. So it's HM tau star. And down here we've got HM of Sn Z mod 2. Yeah, I promised to be precise here, so let me draw it again. M, and here it's N up here. Okay. And here again I've got the transfer homomorphism, or its induced homomorphism in homology. And, right. And now remember, at the beginning in our long exact sequence, we also had verified that this transfer homomorphism is an isomorphism. So just let's convince ourselves that we actually did this. Whoops. Yeah, that's this statement here. Yeah, so in the beginning we showed that this morphism here in our long exact sequence is actually an isomorphism. So let's go back. So this morphism here is also an isomorphism. And now we're almost done. So Hm of Sm, this we just discussed with Roman, that's Z mod 2. So actually this is a composition of isomorphisms, so this must also be Z mod 2. So in this square, actually this composition is just, if you want, the identity of Z mod 2 after identifying it in this way. But this is absurd. Whoops. Which is absurd in case actually m should be smaller than n. So if n is bigger than m, absurd. If n is bigger than m, because then the mth homology of the n sphere is 0. Yeah, so if the dimension of this first sphere, n, is bigger than this m, the dimension of the second sphere, then actually this, let me just write it maybe dashed. In this case, that n is bigger than m, then this would just be the 0 object, and what we would have done is we would have factorized the identity of Z mod 2 through 0, and this is not possible. So that's a contradiction, so the condition n bigger than m is wrong, and its negation is true, so n is at most m, less or equal m, and this is what we wanted to show.